So this is the second of 4 videos on the center of mass. And in this particular video, I would like to talk about the center of mass for two-dimensional systems. Because in the last video, we talked about the definition of center of mass, and we focused on a one-dimensional system. Now, the way this is different is because I now have not just the origin, but I have to worry about an x distance and a y distance. So that's why we're going to talk about the moment of the system about the y-axis and the moment of the system about the x-axis. Now, the moment of the system about the y-axis is represented by my. The moment about the system, the moment of the system about the x-axis is mx. Now, these two are very different things because if you think about it, when I talk about the x's and the y-axis, what we're talking about here is, let's say I have a point right there. If I want to find the moment of the system about the y-axis, I'm figuring out how far it is from the y-axis. So I'm actually looking at the x-coordinate of it. So that's actually what we're going to do is, in this situation, I'm going to look at the summation of all of my individual points. And what I'm going to do is I'm going to take their mass times their x value. I know that seems a little bit backwards, though, is we're finding the moment of the system about the y-axis, and we're using the x value. It's because we're measuring the distance from the y-axis. Again, y-axis, looking at x value. So the question is how does this change if I look at it from the moment of the system for the x-axis? Well, I'm going to look at the distance from the x-axis, which gives me the y-coordinate. So that means I'm going to use the summation, same kind of idea. I'm going to add up all of my individual pieces, but I'm going to take the mass times the y value. So again, it switches. If you're finding the moment of the y-axis, you're going to use x values. If you're using the moment of the system about the x-axis, you're going to use y values. However, the same idea is still going to kind of apply for the center of mass. If we do x bar, y bar, those are going to be my center of mass coordinates, x bar being the average, y bar being the average. What I'm going to do is I'm going to take those x coordinates, so my, and I'm going to divide it by the total mass, m. So notice I'm using all of these x values to find the x coordinate, and I'm going to use all of my y values, so mx, for all of my y averages. So again, it's going to make a little more sense if I write it in this summation notation. We're doing m sub I times x sub I divided by just m sub I. And that's going to give me my x coordinate. And if I do the y coordinate, that's going to be m sub I times y sub I all over m. So again, it seems a little backwards, and it kind of is backwards, but we're talking about distance from that axis, and we're going to use the appropriate coordinates. So I'm going to kind of move on to this first example that I have of this, where it says find the moments of the system and the center of mass for the system objects that have masses of 3, 4, and 8 grams at the points -1, 1, 2, -1, and 3, 2, respectively. I put those in order. These distances are measured in meters, so notice the 3 is at -1, 1. There's the 3 at -1, 1, etc., etc. So 4 is at 2, -1, which I have, and 8 is at 3, 2. Notice I still try to draw these kind of a bit to scale, so the 3 is the smallest, 4 is the middle, and the 8's definitely going to be the biggest. And so again, what that mass of 8 is going to do is it's going to pull the center of mass towards it. It's going to act like a big ball of gravity. So what we're going to do again for my is we're going to find the sum of all of the mass points, in this case from 1 to 3, of mi times xi. So I'm going to use this as 3, my first, times -1, the first x value, plus 4 times 2, the second x value, plus 8 times 3. So again, notice I'm taking the masses 3, 4, and 8, 3, 4, and 8, and I'm multiplying that by the corresponding x value. So think about it. 3 times -1 is going to give me -3. 4 times 2 is going to give me 8. And 8 times 3 should give me 24. And I'm just using my calculator to make sure I add everything up correctly. 24 and 8 should give me 32. Minus 3 should be 29. So that's my, 29. And what I'm going to do for mx is I'm going to kind of do the same thing, just instead of using the x coordinates, I'm going to use the y coordinates. So it's still going to be 3 plus 4 plus 8, and all I'm going to do is switch it out for the y value. So 1, -1, and 2. So 3 times 1 gives me 3. That's going to be -4. That's going to be plus 16. 3 minus 4 gives me -1 plus 16 gives me 15. So again, we're looking at summing up mi times yi, which is 15. And the last little bit of information that I need to do for the center of mass is, again, I need to take those coordinates that I found, or those weighted averages that I found, excuse me, and divide by the total mass. So I'm going to take 29 and 15 and divide those by my total mass, which was 3 plus 4 plus 8. 3 plus 4 makes 7, plus 8 makes 15. So we're just going to do 29 divided by 15 and 15 divided by 15. So let's see if I do the calculator. 29 divided by 15 gives me 1.93 repeating. 15 over 15 is, of course, 1. So there is my center of mass. So notice again, at 1.93 comma 1, that's almost at 2. It's right about there. There's my center of mass. Again, like I said, that mass of 8 acts like a big ball of gravity, and it's pulling the center of mass towards it. Now, the other thing that I want to talk about is, because these are what I would call discrete systems, because it's a collection of points like a scatter plot. What happens if I make it a little bit more continuous? So in that situation, we call it a lamina, which is the thin surface of uniform density. So something you think about is more or less a plain board or a sheet of metal, or a piece of paper. It's a thin surface of uniform density, and this symbol is a Greek symbol called rho. It looks like a P without the stem, and it's often represented by a two-dimensional figure, a plane, some kind of shape. And the center of mass of a lamina is called the centroid. Centroid. The other thing I want to mention to you about lamina specifically is that if we have a region R that is symmetric about a line L, then the centroid has to lie on that line of symmetry, and that's called the symmetry principle. And that is actually pretty useful when we have symmetric regions, like, for example, this one I have down here, where we have a rectangle formed by the lines x equals 6, which is this line right here, x equals 6. It goes up and down. Then we have the horizontal line y equals 2, and it's in the first quadrant. So here we have a nice, beautiful, symmetric region. And so really and truly, all I have to do is, since it's a lamina, which is uniform in density, its center of mass should literally be in its center. So I'm going to look for its center, its line of symmetry, which there's the vertical line of symmetry, splits it in half, and the horizontal line of symmetry goes that way. And so right there, right in the center of this lamina, right in the center of this rectangle, is going to be my center of mass, or my centroid, which is at the coordinates 3, 1. So notice the center of mass happens to lie on both of those lines of symmetry. So hopefully this helps. Please feel free to let me know if you have any questions. I will see you all again in the third video. Have a great day.